Hello, today we are going to look at a very special exponential equation that arises in ecology. And this is the logistic growth equation. This equation allows us to model population growth as a factor of time. So the general equation is P of t, so the population at time t, is given by A divided by 1 plus B times e to the negative RT. A lot of these numbers, if not all of them, will be given to us in the context of an equation, but it's worth discussing what they represent. So A is the carrying capacity. And if we were to graph this function, we get a curve that looks like this. As time goes by, the population increases rapidly, and then the increase slows down as it gets to this upper limit. That is the carrying capacity. It's the number of individuals in a population that a given environment can support with its limited resources. B is a constant that is found using the original population. Again, it's often given to us. R is the growth rate. So notice that we have a negative sign there. So R is still positive when it's growing, but in the equation, it turns negative. If we have a population that's decreasing in size, R would be negative, which means when we plug it into the equation, it would become positive. The reason why this works isn't something we need to go into right now, but it's worth remembering that we'll often see a negative sign in here, even though our population is growing. So let's do an example of logistic growth. So for a specific species, we are told that its population can be modeled as 700 divided by 1 plus 6 times e to the negative 0.03 t. So this says our growth rate is 0.03 or 3%, and the carrying capacity is 700. If we were to plug in 0 to the equation, we could find the initial population. So the initial population as time equals 0. Before I go further, though, I should mention that this equation has time measured in years. No, excuse me. See, I should really look at my notes a little bit more closely. This one has time measured in months. The question has years. We'll see that in a moment, getting ahead of myself. So P equals 0 months. So P of 0, 700 over 1 plus 6 times e to the negative 0.03 times 0. Well, we can simplify this really quickly. Anything times 0 is just 0. And then anything to the power of 0 is just equal to 1. So we have 6 times 1. 6 times 1 is just 6. And 1 plus 6 is 7. So the initial population size was 100. Now the first question, is how big is the population after 2 years? Now we have to be careful here because what did I say the units actually are? Months. So because our units are in months, we have to convert this 18 years, or excuse me, this 2 years into months. And if there's 12 months in a year and there's 2 years, we're really interested in plugging in 24 months so that our units match our equation. If we just plug in 2, our answer will be incorrect because we're not adjusting the units accordingly. So we'll plug in 24. And so we'll have 700 over 1 plus 6 times e to the negative 0.03 times 24. We could simplify this step by step and put into our calculator one piece at a time, or we could just plug it into our calculator, and it's approximately equal to, let's see, where do I have it written down? 470.8. Now, hopefully when you saw that, you got a little uneasy, because this represents population. Can we have 0.8 of something? Probably not if it's living. So we always need to round our answers to a whole number. So we would say our population is 471 individuals. If we had 470.3, we could round down, but our standard rounding rules say if our decimal is above 5, round up to the nearest whole number. So these are like the easy questions we could ask, where we just have to plug in a value for t. The more interesting question is how long it takes to reach a certain size. So let's say we want to know how long until the population is equal to 650 specimens. So we have a population of 650, which is pretty close to our carrying capacity. And if we remember that curve, as we get closer to that carrying capacity, things are going to slow down. So it might be a small amount of time. It might be a large amount of time. We won't really know until we solve it. And these equations can look intimidating. So I really want you to stay with me, pause the video at each step if you need to make sense of things, but we can get through it together. So we're told P of t is equal to 650. So we are going to plug in 650 to our equation. And this looks really awful because our variable's down in the denominator. And what am I going to do? It's actually incredibly simple. Just multiply everything by the denominator. So in one step, we go to 650 times 1 plus 6e to the negative 0.03t equals 700. And now we don't have any more fractions. That's completely legal to do in math, and it saves us a lot of work. Now we could distribute this, but I don't want to have to multiply more numbers than I need to. So instead, let's just divide both sides. So we have 1 plus 6 times e to the negative 0.03t is equal to 700 divided by 650. And I've done all this work off to the side to make sure I've got my numbers right. And this reduces to 14 over 13. The next thing we have to do is subtract 1 from both sides. But I have to make sure it's a common denominator. So over here, I'm going to subtract 13 over 13. So I have 6 e to the negative 0.03t. And then we get to 1/13. And now we need to divide both sides by 6. So let's see. I don't like dividing a fraction. So let's instead multiply by 1/6 on both sides. And so this will give us e to the negative 0.03t equals 1 times, well, look at that. I made a careless mistake in my solutions. So when all else fails, grab your calculator. So 13 times 6 is 78. And now that I've gotten down to here, we can write this in log form. So we have the natural log of 1 over 78 is equal to negative 0.03 times t. And then we have to divide this, so t is equal to the natural log of 1 over 78, all divided by negative 0.03. And now, back to our handy-dandy calculator. I want to do 1 divided by 78. And then where's my natural log button? Right here. And then I get to divide this by negative 0.03. That's strange. So, funny story. While I figure this out properly, when I left work before schools were closed, I unintentionally left my very handy scientific calculator in the desk in my classroom. And now schools are closed, so it's stuck. But if I've done this correctly, that is a large number. We get 145.2 months. That's a lot of months. In fact, if we round it to the nearest month, 145 divided by 12 months in a year, that is just slightly more than 12 years for this population to reach 650 individuals. So, logistic growth is powerful, and it can tell us a lot of different things. Now, you might be wondering, could this tell us how many people will get the coronavirus? Unfortunately, no, because the spread of a virus doesn't have a carrying capacity. In theory, everyone could get the virus. So this is more along the lines of how many wolves in the habitat, because they're an endangered species, or how many polar bears in the Arctic. So species that rely on resources in order for their populations to grow. Although these questions require a lot of steps, they are fairly straightforward if you break it down piece by piece. So even if it looks intimidating, don't be intimidated. Just follow it one step at a time.